Next, we're going to look for combinatorial constructions corresponding to labeled objects called words. And these are another way to look at the strings that we considered in the last lecture. And again, there's many more details on applications, motivating applications and results in part one of the course. In this part, we're going to focus on the math and on the analytic combinatorics to show that the symbolic method works for a broad variety of combinatorial classes. So last time we talked about strings. It's a sequence of n characters drawn from an m character alphabet so that there's m to the n different strings. And it's just a sequence of characters. This time we're going to talk about that same object, but we're going to look at it as a word. So it's a sequence of m labeled sets that have n objects in total. There are also m to the n words, and so it's a sequence of sets. Now these are really two different ways of looking at the same object, because if you take the string and you take every occurrence of the letter I as being the ith set in a sequence. So for example, 1 in this string appears in position 7, and that's the only place it appears, so that corresponds to the set 7. 2 appears in 1, 3, and 8, so that corresponds to the set 1, 3, and 8. There's no 3. 4 appears in position 2 and 4, and 5 in positions 5, 6, and 9. You can see a direct correspondence between strings and sequences of sets. We refer to sequences of sets as words. So that's the correspondence, again, just what I just described. So what's the difference between strings and words? There's no difference. It's only the point of view. Last time when we talked about strings, we were concerned about sequences of characters in relation to one another in the sequence. Like how many sequences of zeros in a row are there, or does a pattern occur? For this lecture, in words, we're more concerned with the sets of indices and not so much in the sequence. And there's applications where that point of view is the one that we want to push. So another way to look at the same thing is a balls and urn model, which is classical in combinatorics. So if we have n labeled balls and we throw them into m urns, you can think of when ball I goes into urn J, that means the j character in the string is, the ith character in the string is J. So when 5 goes into urn 1, then we just write a 1 in the string. So this balls and urn sequences is simply corresponds to strings. And we don't care about the order in which the balls are in the urns. They're sets of indices. So balls and urn sequences are equivalent to both strings and words, and so sometimes we use that model for describing these objects. But it's more like words in terms of its a sequence of sets of objects. So how many words are there? Or if you throw in balls to m urns, how many configurations are there? Well, you can tell by the language that I'm using that this is going to be very simply described with a symbolic method. So we'll call the combinatorial class W sub m. So that's we have a sequence of m urns. And then the size function is just the total number of objects. And so the generating function is straightforward from the definition. And so we've got all those examples that I just talked about, but the key thing is that the combinatorial construction says that a word on m letters is a sequence of m urns, a sequence of sets. And so the generating function, the set of objects is e to the z, sequence of size m is that to the mth power, so the generating function is e to the mz. Coefficient of z to the n in that times n factorial is m to the n. So that's the basic construction and counting for words. And again, using the standard paradigm, we can build off this same construction to study variations, and there's many important applications of variations. But again, just to summarize, a string is we think of as unlabeled objects that are just a sequence. We use OGFs, and our enumeration is it's a sequence of m different unlabeled objects. So the generating function is 1 over 1 minus z m to the n. That's what we talked about last time. And we use that to study algorithms like string searching algorithms. Whereas a word is labeled objects, it's exponential generating functions, it's sets of objects, but you could also write it as a string. The construction is a sequence of sets of objects of size m, and we get the same count, and we use that to study hashing algorithms and more generally occupancy problems in combinatorics. But we can do variations, again, just as for permutations, to get results for problems, applications problems, using the same symbolic method that we use for the basic problem. And these are two very famous variations. And again, if you want to see many more details about these, go to part 1 of the course. So a birthday sequence is a word where no letter appears twice. We throw the balls in the urns and we never get 2 balls in an urn. A coupon collector sequence is a word where every letter appears at least once. So birthday sequence is about if you have a room with n people in it, and and there's 365 different birthdays, what's the chance that no 2 people have the same birthday? Coupon collector sequence is how many things do you have to see before you get everything in the collection. And there's many, many applications of both of these. And they're classic in combinatorics. So let's look at a simple modification of that basic construction to study the problem of how many birthday sequences are there. So that's words where no set has more than 1 element. Again, it's easy to define the class and the generating functions, and the construction is simply a birthday sequence with alphabet m letters is a sequence of length m of either empty urns or urns with 1 ball in them. So that means the EGF of birthday sequences is just 1 plus z to the m. And the counting sequence is coefficient of n factorial times coefficient of z to the n in that, which is m times m minus 1 and so forth. And then if you want to get the probability that random word's a birthday sequence, divide that by m to the n and so forth. So that's, again, just a simple example of modifying the basic construction to be able to quickly get a generating function for such sequences. Or another example is coupon collectors at the other end of the spectrum. So that's a string that uses all the letters in the alphabet. So it's a sequence of sets, none of them are empty. So by now you can practically write down this construction yourself. A birthday sequence is a sequence of length m of sets that are all of size bigger than 0. The transfer theorem immediately gives a generating function equation. So a set of size greater than 0 is e to the z minus 1. Subtract off the first term, the set of 0. And then sequence of m of those is e to the z minus 1 to the m. So that's a generating function that describes for the coupon collector sequences exponential generating function. And so here's some other related combinatorial classes. Another name for a coupon collector sequence is an M surjection. That's an M word with no empty set. If we take off the constraint on M and you just say it's a word that's an M surjection for some M, so that is there's some value of M that it's a sequence of sets, none of which are empty for some size of the sequence. So these are examples of surjections. So how many surjections are there of length n? So this one's all 1s, this one's all 1s and 2s, and then the rest of them are 1s, 2s, and 3s. But from analytic combinatorics, it's easy to write down the construction for this. For M surjections, we had sequence of length M, and we got that generating function. For surjections in general, we take out the constraint on M. So that means the set greater than 0 is e to the z minus 1. Sequence of those is 1 over 1 minus that. So it's 1 over 2 minus e to the z. That's the generating function for surjections. Now to extract an estimate for the coefficient of z to the n in that, again, it's best done with complex asymptotics that we'll talk about in the second part of this course. Turns out to be about n factorial over 2 log 2 to the n plus 1. Again, a very simple modification to the basic construction, but it leads us to a generating function equation that we can later analyze. And by the way, the analysis at the other end is going to have come from similar general transfer theorems. So this is the types of variations that we see on words. So we start with the basic construction, so maybe we generalize it to talk about coupon collectors, where we insist that all the letter counts are bigger than a certain amount, or a birthday, where all the letter counts are less than a certain amount. And these things are relevant in the analysis of computer algorithms and many other applications. Or you can do the constraint really in any way, that you want the occupancies to all be odd or all be even or prime numbers, whatever you want. It leads to a generating function equation. And then we talked about surjections. So again, starting with a basic thing, we get a galaxy of related constructions. That the constructions are quite simple, and they lead to generating functions of all different character. And that's an introduction to the analytic combinatorics of words and strings, and how to use the symbolic method to get exponential generating functions for a variety of combinatorial classes.